Hey guys! In today's video, we're going to be looking at Chapter 8, Lecture 18, Learning Objectives 3 through 5. So we're going to be looking at the proper way to draw a Lewis structure. We're going to be looking at electronegativity, and we're going to be looking at charge separation. So when we make a bond in a covalent substance, so bonds in covalent substances, the goal is to get that substance to get octets for all the atoms within there. So our goal, octets for all. There will be examples where we will not try and do this. For instance, hydrogen, helium. Hydrogen and helium are good already. They've already got their noble gas configuration, or in the case of helium, or in the case of hydrogen, they only need one electron to get to that noble gas configuration. So they're not going to try and get an octet. They're only going to try and get 2 electrons, as that is what their outer shell will hold. But when we're talking about most others, we're trying to get an octet. So octets for all the atoms. And it can do this in covalent bonds by sharing electrons. So when 2 nonmetals share electrons, they both get to use those electrons to contribute to their octet. Okay, so we could have, for instance, if we have 2 nuclei, we have what's called the inner nuclear axis. Is right here. And that's where our nuclei kind of sit, is right there. And then in between the inner nuclear axis, in a bonded pair of electrons, or in a bond, we have 2 electrons, where generally the electron density is between those 2 atoms. So the 2 electrons will be shared between those 2 atoms, both of them getting closer to a octet. The bond length is the length between these 2. And we call the bond length, it's going to depend on attractive and repulsive forces within the atom, or within the atoms within the bond. So the length depends on the attraction between the electrons of one atom with the nucleus of the other, and it also depends on the repulsion of the electrons of both atoms. So our electron-electron repulsions. Along with proton-proton or nucleus-nucleus repulsion. Okay, so the bond length itself is the balance between attractive and repulsive forces. Okay. The way that we show these bonds within a molecule is with a Lewis structure. So the bonds, those sharing of electrons, are depicted within a Lewis structure. A Lewis structure is going to show all bonds and what types they are, along with any lone pair electrons, and then of course the atoms that make up the molecule. So a Lewis structure of a molecule contains the molecule's atoms, so it's the molecule's atoms. It also includes all the atoms, electrons. So, well, specifically valence electrons. So no core electrons. So within here, our electrons can be as bonds, so pairs of electrons, or as lone pair electrons. Again, these are in pairs, but these are non-bonding electrons. So they will not be in between two nuclei on the internuclear axis. So those are the two we generally look at. We can also have radicals. So if you've ever listened to any infomercials, you've probably heard of radicals. Radicals are unpaired electrons. Okay. And again, our goal here is to try and get a structure where the atoms within there have an octet, except for things like hydrogen. Okay. So we can look at something like NH3. If we were to draw NH3, we could start out actually with our Lewis dot structures. And we see that these two can share, and share. And that can share. And what we can see is that anytime we have two electrons between two atoms, they form a bond. So these, and these will all form bonds. Well, this is not in between two atoms, so it will not form a bond. And what we get is that right there. Okay. So what we see here, what we see here is these are our non-bonding electrons, and then these are our bonding electrons or our bonds. And in both cases, we see that they are in pairs. Now, we can have what we see here, which are single bonds. So a single bond is one pair of electrons shared between two atoms. If we share more than one pair, we get what's called a multiple bond. So a multiple bond is two or three pairs of electrons shared between two atoms. Okay, so if we have two pairs, this is called a double bond. If we have three pairs, it's called a triple bond. So we can see the double bond in something like carbon dioxide. So here are two lines. That equates to 4 electrons or 2 pairs of electrons. So our double bond. Our triple bond, we see this in cyanide. Right here. Here is our 3 lines. That equates to 6 electrons or 3 pairs of electrons. Okay. This is kind of just an overview, but let's look at how we actually draw our Lewis structures. So we're going to go through these steps to form Lewis structures. Okay, so what to be given is some sort of chemical formula, CH4, NH3, something like that, where you're given the atoms in there and you're told to draw a Lewis structure for those atoms. So our very first step is to find out what our electron pool is. So we're going to sum up the valence electrons from each atom in the molecule. Okay. Now, if we have an ion, we have to take that into account when we think about our electrons. Remember that if we have a cation, that means we have too few electrons, or we've removed electrons. If we have an anion, that means we've added electrons. So for a cation, you remove electrons equal to the magnitude of the charge. So if you have a 2 plus molecular ion, then you would take away 2 electrons. And then if you have a molecular anion, you add electrons. Equal to the magnitude of the charge. So if you have a molecular ion that's 3 minus, then you take and add 3 electrons to your sum or your pot of electrons, whatever you want to call it. The next step is you're going to write the symbols for the atoms, and you're going to take into account the atom connectivity. So you're going to show which atoms are attached to which. Okay, so what atoms are attached to what? This requires a little bit more explanation. So whenever you're given a chemical formula, generally the atoms are written in the order in which the atoms are connected. Excuse me, the atoms are written in the order that they are connected. Okay? And there are, most times for this class at least, there will be a central atom. So most of the molecules we will look at will have one central atom, where every other atom is connected to that central atom. The central atom is going to be the one that is least electronegative, with the exception of hydrogen. We exclude hydrogen because hydrogen is never a central atom. Hydrogen can only make one bond, and because it can only make one bond, it cannot have multiple atoms attached to it, therefore it cannot be a central atom. Please, 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 do not put hydrogen as a central atom. Okay, after you have written the central atom, you will put the other atoms surrounding the central atom, and you'll add lines connecting those atoms. So we will draw lines connecting the central atom with the other atoms, which are called peripheral atoms. So connecting the central atom to the peripheral atoms. Okay. Now, we have this pool of electrons, and now we've written lines. Those lines are electrons, so we need to subtract the electrons from our bonds from our pool of electrons. So subtract bond electrons. So the lines where each line is equal to 2 electrons from the electron pool. So it's the first thing we've removed from our electron pool. After we've done that, so step number 2 was very long. Next is step number 3. Sorry. We're going to complete the octets around all other atoms except for the central atom. So we'll complete the octets of the peripheral atoms. Again, we're going to exclude hydrogen from this. If we have hydrogen, it's good with just a bond. That gives us its 2 electrons. It is set. Again, subtract all the electrons you added from the electron pool. And then if you have any leftover electrons, you're going to place those leftover electrons around the central atom. And then you're going to keep doing this until you run out of electrons. If you find, okay, I think that's it. So I will see you guys in the next one. Bye. Now, once we have our values in Coulomb and meters, we actually do need to get all of these into the same unit. So we will use our conversion from debye into coulombs, which will allow us to cancel that out. So if we have debye's, 1 debye is going to be equal to 3.34 times 10 to the negative 30 coulombs times by meters. So we can convert our debye's into coulombs when we use this equation, or we can convert our coulombs into debye's in order to use this equation. The other thing that we will see a lot of times with this equation is the use of the electronic charge. So the charge on 1 electron, or it could also be considered the charge of 1 proton. Just depends on the sign. If you have a negative to this, it's an electron. A positive is the proton, but I'm just going to give you the magnitude of it, which is 1.60 times 10 to the negative 19 coulombs. If this value is negative, we're talking about the charge of electron, 1 electron. If this is positive, we're talking about the charge of 1 proton. So putting those all in, we can solve for our dipole moment or our magnitude of charge. For instance, let's try an example. Let's say we have Hi, hydrogen iodide. Hydrogen iodide has a bond length of 1.61 angstroms. It has an electronegativity difference of 0.4, and it has a dipole moment of 0.44. Those values should be very, very similar. We can figure out the charge on both of our species by using this equation. So we want to go ahead and put our angstroms into meters. Remember that 1 angstrom is equal to 1 times 10 to the negative 10 meters. So this will be equal to 1.61 times 10 to the negative 10 meters. And then we want to put our dipole moment from debye's into coulombs. So we're going to take that 1 debye is equal to 3.34 times 10 to the negative 30 coulombs times by meters. And what we get is 1.47 times 10 to the negative 30 coulombs times by meters. And then it can all be placed into this equation. 1.47 times 10 to the negative 30 coulombs times by meters is equal to our Q times by 1.61 times 10 to the negative 10 meters. And we get a value of Q equal to 9.13 times 10 to the negative 21 coulombs. Now, this doesn't tell us a lot. We want this to be an actual electron charge. So we want to take this and convert it into our electronic charge, where E is equal to 1.60 times 10 to the negative 19. So that E is that electronic charge. And this gives us a value of 0.057 E. So it's, if we had a full 1, we would have transferred an electron. But we did not, so we would say that our hydrogen has a 0.057 positive, and then our chlorine a negative 0.057 electronic charge on it. Okay? Okay, that really is it. And I will see you guys later.